Hi, my name's Jenna Saylor, and this is my Physics 2212 lab report on lines of charge. Purpose of lab: to observe the interactions between two charged pieces of clear tape, to produce a computational model of two charged tapes with an evenly distributed charge, to find the magnitude of charge on a singular piece of tape through the computer model, and to further analyze the results and answer the comprehension questions. Preview: the initial conditions of the tape were as follows. The experimental results were negative 2.3 times 10 to the negative 6. The electric force, then gravitational, was 1.96, and the charge was 2.304. And then for the computer results, they were pretty similar. The electric force was 0.137. The gravitational force was 1.92 e to the negative third, and then the charge of the tape was the same. Some important concepts to understand are the Coulomb force, which is the force between two different charges. So it's K times both charges over the magnitude squared times the unit vector. And then also just gravitational force, force equals mass times gravity. And then the electric field, which is very similar to the Coulomb force, except it's the interaction between an observed point and then one singular charge and just the electric force of that. Also, one more thing on the Coulomb force, it is the electric field times the charge. So similar. Okay, then once again, just quickly going over the experimental procedure. This was the same as in lab 1, but basically you cut two pieces of tape similar length and you put them on each other and quickly pull it off. So one of the tapes will be charged. You know if it's charged if you hold your hand near it and then it attracts or repels it. And then you do this again so you have two charged pieces of tape. And then down over here I just have some images. If it's the same charge, they'll repel. Different charges, they're going to attract. And then neutral, no interaction. So just again, quick review of the experiment results. The tape was attracted to the hand after ripping. Two of the charged tapes will repel each other, and they're attracted to a neutral object. And then down here, it's just showing the force, how the tape floated above each other. But this is more lab 1 rather than lab 2, so I'm not really going to get into it. But now time for the computer model. So there was already a starter code, but I had to go ahead and edit a few things. So right here, I just added in the gravitational constant and the K constant. Then down here was just the mass of the tape and the charge of the tape that we calculated in the actual experiment. Down here on line 34, I created a function to calculate the electric field. So it was just R, which is observed location minus the source. And then I found the magnitude and the unit vector of that and just plugged it into the electric field formula that we discussed on the previous lines. Over on the right, on line 49, this was already in the code, but I had to just go ahead and edit a few things, but it just gives the total charge on the tape and kind of spreads it out. And then down here, it was just plugging the top tape and the bottom tape into the electric field function to find the fields for each one. And then there's also some code for an arrow and vector so we can just see where the fields are pointing. Once again, gravitational field. And then down here is just printing the results. So here we can see the results. The green one is the top tape, or the red. The greens are a bunch of little arrows, and the blue is the bottom tape. The magnitude, gravitational force, and the charge is what we had on the first slide, our results. So now the charge of one piece of tape by the computational model was 2.304 times 10 to the negative 6. And some of the assumptions that we had to make prior to the experiment was no air resistance, because we're assuming this is in a perfect environment. And then also that each tape that we had in the true experiment was the same amount of charge and it was evenly distributed along the length of the tape, which allows us to compare it to our computer model. So what if why? What if we had modeled each of our tapes as a single point charge like in the previous lab? And compare this to the ones for the full length that we did in this. So as a point charge, the estimated value was negative 2.304 compared to the value of 0.18374, which was the line charge. So the line charge has a much larger magnitude than the point charge. And then finally, why do the estimates differ? Which one is more likely to be closer to the real value? So once again, the estimates differ because they're different models used to find. The point charge is more concentrated, while the line charge is more generalizable to real life. So the line charge is closer to the real value because it follows ideals of superposition, which is taking a bunch of tiny little points and calculating each individual field and then adding them all together. And just like calculus, when you break it into smaller parts in infinitely many small parts, it's going to give you a more accurate answer. So for errors, I definitely have limited coding experience. As you can see, my observed and computer model electric field were a bit different. Although it is correct in the sense that the computer model should have had a larger value, it was probably too large. So if I were to redo this experiment, I would make sure that was better. The tape also in the experimental model could have had contact with other surfaces, neutralizing it. I could have used more precise numbers, did more different parts in superposition, and then finally there could have been air resistance.